Thermodynamic Lecture 3 Adiabatic process. Adiabatic process, a process by taking place in a thermodynamic system from which there is no exchange of heat between the system and its surrounding. Adiabatic process is very fast process according to which P V gamma is equal to T V gamma minus 1 is equal to T gamma by P gamma minus 1 is equal to constant. We know dq is equal to n c dt, and c is equal to adiabatic process 0, dq also 0. Molar heat capacity of adiabatic process is 0. From first law, dq is equal to n c dt. Work done by system is equal to decrease in internal energy. When a system expands, adiabatically work done is positive. Hence, internal energy decreases. A system cools down and vice versa. The work done in a adiabatic process in a adiabatic process W is equal to N R T initial minus T final by gamma minus 1 is equal to P initial, V initial, P final, V final by gamma minus 1, where Ti is equal to T initial and T F is equal to T final temperature. Let us take an example. Sudden compression or expansion of a gas in a container with a perfectly non-conducting wall. Suddenly bursting of tube of a bicycle tire. Propagation of sound wave in air and other gases. isobaric process. A process taking place in a thermodynamic system at a constant pressure is called isobaric process. And a molar heat capacitor process taking place Cp and dq is equal to n Cp dt. Internal energy du is equal to n Cp dt. From first law of thermodynamics, we get dq is equal to du plus dw. dw is equal to p dv is equal to nr dt. Process equation v by t is equal to constant. Then isobaric process. A process taking place in a thermodynamic system at a constant volume is called isobaric process. Volume is constant. dq is equal to n c v dt. Molar heat capacity of isobaric process is Cv. Volume is constant, so dw is equal to 0. dw is equal to 0. The process equation P by T is equal to constant. Cyclic process. When a thermodynamic system returns to initial state after passing through several states, then it is called cyclic process. Cyclic process N is equal to work done by heat supplied. Work done by a cycle can be computed from area enclosed cycle PV curve. volume elasticities of gas. There are two type of volume elasticities of gas: isothermal isothermal modulus of electricity ES is equal to P. Adiabatic modulus of electricity ET is equal to gamma P. Ratio between isothermal and adiabatic module ES by ET is equal to gamma is equal to Cp by Cv, where Cp and Cv are specific heat of gas at a constant pressure and constant volume. For isothermal process, delta T is equal to 0, therefore specific heat C is equal to delta Q by m delta T. For adiabatic process, second law of thermodynamics. The second law of thermodynamics gives a fundamental limitation to efficiency of heat engine and the coefficient of a performance of a refrigerator. It is said that efficiency of a heat engine can be never be unity, means 100%. This implies that heat released to cold reservoir can never be made zero. Kelvin statement. It is impossible to obtain continuous supply of work from a body by cooling. It is a temperature below the coldest of its surrounding. Calcius statement. It is impossible to transfer heat from lower temperature body to higher temperature of a body without use of an external energy. Planck's statement. It is impossible to construct a heat engine that will convert heat completely into work. All these statements are equivalent as one can be obtained from the other. Entropy. Entropy is a physical quantity that remains constant during reversible adiabatic change. Change of entropy is given by ds is equal to delta q by t, where delta q is equal to heat supplied to the system, and T is equal to absolute temperature. Entropy system never decreases. Means ds greater than 0. Entropy system increases is an irreversible process. Irreversible process, not reversible. Heat engine. A heat energy engine is a device which converts heat energy into mechanical energy. A heat engine consists of three parts: source of heat at a higher temperature, working substance, sink of heat at a lower temperature, thermal efficiency of heat engine given by N is equal to work done per cycle divided by total amount of heat absorbed per cycle. Efficiency is equal to 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. Q is the heat source absorbed from heat source. T1, T2 are the temperature source of a sink. Heat engine have two types. One, external combustion engine. In this engine, fuel is burnt a chamber outside the main body of engine. Example, steam engine. In particular practical life, thermal efficiency of a steam engine varies from 12 to 16%. Then internal combustion engine. In this engine, fuel is burnt inside the main body of the engine. Example, petrol engine or a diesel engine. But practical life, thermal efficiency of a petrol engine is to 26% and a diesel engine is 40%. Then Carnot's cycle. Carnot divide an ideal cycle operation for a heat engine called Carnot cycle. The net work per cycle of engine Q2 by Q1 is equal to T2 by T1. The efficiency is N is equal to 1 minus T2 by T1. This is the efficiency of the cycle. The efficiency of Carnot cycle maximum for giving temperature T1, T2, but because many ideal situations have many assumed while designing engine can be practically not obtained. Refrigerator or heat pump. A refrigerator or heat pump is a device used to cooling things. It absorbs heat from shrink at a lower temperature and reject a large amount of heat to source up at higher temperature. The coefficient of performance of refrigerator beta is equal to Q2 by W is equal to Q2 by Q1 Q2 is equal to T2 by T1 T2, where Q is the absorbed heat from shrink Q1, Q1 the heat is rejected to source, T1 T2 are temperature of source and shrink. The relation between efficiency and the coefficient of performance beta is equal to 1 minus